In this video, we're going to talk about how to use the quote-unquote inverse trig functions to help us to solve equations that have sine and cosine in the equation. Solutions to equations. Now, heads up, y'all. If you're in my Math 142 class this term, there is definitely going to be a question on an exam where I say, what is a solution to an equation? When I say, what does it mean to solve an equation? And if you don't give me this definition, or something that is logically equivalent to one of these two definitions, you're not getting the points on that question. Okay? So take notes. A solution to an equation is a number which can replace the variables in the equation and after doing so, the resulting equation is a true statement. For example, x equals 3 is a solution to the equation x squared is equal to 9. How do I know that that is the case? I know it's the case because if I replace the x with a 3, I get 3 squared equals 9, and that is certainly a true statement. 3 squared, yes, that is in fact 9. Now, what does it mean to solve an equation? Solving an equation specifically means finding or describing all possible solutions. If someone asks you to solve an equation, finding one solution is not enough. You need to describe all of the solutions, all of the numbers which make that equation true. For example, if someone says solve x squared equals 9, it is not enough to answer x equals 3. This is certainly one solution, but it is not all of the solutions. To solve this equation, I would have to describe both of the two solutions, x equals 3 and x equals minus 3. Both of these numbers make this equation true. Okay, so I hope you've got that written down. Literally, I promise you, this will be on the exam. Okay, so 2 videos ago, we established the fact that the square function is not invertible because its graph does not pass the horizontal line test. And as a result of that, it didn't have a true inverse, but it had sort of a fake inverse, which was called square root. Now, the square root function can help us to find one solution to an equation like x squared equals 9. One solution is given by the output of the square root. Square root 9 is equal to the solution positive 3. But to get all solutions to actually properly solve this equation, I need to use the square root tool together with another tool, plus minus. This will get you plus or minus 3, and that will get me the two solutions, positive 3 and negative 3. Now, when I'm solving an equation that has a trig function in it, for example, sine of x is equal to 1, the inverse sine function, the arcsine function, will get me one solution. Arcsine 1 is one solution. But it's not all of the solutions, and therefore to properly solve the equation sine of x equals 1, we need to use another tool to help us to get from this singular solution to getting all of the other solutions. So, to solve an equation that has a trig function in it, for example, something like sine of x equals 1, what technique do we use? First of all, if necessary, isolate the trig function. So you want something like sine of BOP equals number, or cosine of BLOP equals number, or tangent of BLOP equals number. There is nothing on the outside of this equation around sine, cosine, or tangent. Those functions are isolated on one side of the equation. The next thing that you do is use the inverse trig functions to find one solution, but to get all of the other solutions, we'll use the unit circle, and I will show you that process in an exercise. For example, someone wants me to find the solutions to the equation sine of x equals 1 over 12. They want me to find all of the angles at which sine outputs 1 over 12. So step number 1, to get started on this problem, I'm going to use the inverse sine function to help me to find one angle at which sine outputs 1/12. So for this, because the y-coordinate of 1 over 12 does not appear on the unit circle, this is something that we're going to do by calculator. Find one angle using arcsine. So let's find the angle that is equal to arcsine of 1 over 12. So for simplicity's sake, I'm just here on the Windows 10 graphing calculator. And here we are. They're looking for an answer which is in radians. So I'll start by switching to radians mode. And I'll enter the value of 1 divided by 12, which is our input in this problem. Then I'll go to the trigonometry tab, hit second to unlike the inverse sine function, and select that, and it gives me a value of 0.0834. So I think, I can't write down all of this. Let's just go to 3 decimal places. 0.083 radians. Okay. Now this is just one solution to this equation. Specifically, this is the singular angle between negative 90 degrees and positive 90 degrees. Let's see how we would figure out the other solutions to this equation using the unit circle. So here is the unit circle. We are looking for locations where the y-coordinate, where the sine is equal to 1/12. So I'm going to mark y equals 1/12 on this image, and I'm just going to sketch in a line to indicate to me where that height is. So what we have just found is that one angle at which this y value is produced is the angle 0.083 radians. So the question is, what are all the other angles at which this same y value is achieved? Now the first thing that I'm going to remember is that if I have any angle which is coterminal to 0.083, then that will put me at exactly the same position on the unit circle, and therefore y will output exactly the same value. So these are, roughly speaking, half of the solutions so far. The other half of the solutions would correspond to this other location on the far left side of the unit circle, where the y-coordinate is also equal to 1/12, only the x-coordinate is different on the left side. So the question becomes, how do I find the value of this red angle over here on the left side of the unit circle? The thing that I notice about the red angle is that I can reach this location by going forward a full 180 degrees and then going backward by an amount which is equal to the 0.83 radians. So if I turn counterclockwise through an angle pi and then turn backward clockwise by 0.83 radians, that will position me in the direction corresponding to the red arrow that I've drawn. So the red angle says go pi and then go backward by 0.83 radians. So let's get a quick decimal approximation for this value, 3.059 radians. But also, any angle coterminal to this angle would also work. So this entire paragraph here would be my answer to the question, solve sine of x equals 1/12. In order to answer the question, solve sine of x equals 1/12, I need to find or describe all the possible solutions, all the possible angles which makes that true. And that's what I have achieved down here. So this entire thing is the final answer. Now this is a little bit of a mouthful. So what we're going to do next is we're going to look at a slightly more compact way to express the information written here. And in order to do that, the first thing that I want to do is remind us of the definition of an integer. The word integer is referring to a special kind of number. An integer is a whole number, and the number is allowed to be either positive, negative, or 0. So the integers include the number 0 itself, as well as all the counting numbers 1, 2, 3, 4, etc., as well as all the negative versions of those numbers. Basically, fractions and decimals are not allowed when you're working with integers. Now, if you want to refer to the complete collection of all the integers, basically all the numbers in this list, then there's pretty convenient shorthand for that collection, and that is the letter Z with an extra bar on it. So the way that I usually write this is by writing a 7 and then writing an upside down 7. So this would be the stroke order for this particular letter here. Z stands for the German word for integer, Zahlen. Okay, now with this notation, if you want to make the statement that k is an integer or any integer, that is written in shorthand in the following way. K, and then the letter C with an extra bar in it, and then Z for the set of integers. This is shorthand for the statement k is an integer. We can use this shorthand to help us to shorten the answer to the previous exercise. 0.083 or any coterminal angle can be rewritten in the following way. using the fact that coterminal angles are separated by full rotations. I would say 0.03 plus 2 pi, because that's one full rotation, 2 pi times k, to represent that you can rotate in any direction any number of times. 3.059, or any coterminal angle, turns into 3.059 plus 2 pi k. So you can rotate through 2 pi in either direction any number of times, and you'll get a coterminal angle. And we would finish this by saying k is an element of the integers, just to keep somebody from accidentally thinking that you can go half a rotation or a quarter of a rotation. You have to go a full rotation to end up at a coterminal angle. Let's try the same exercise, except with cosine instead of sine, and let's see how our answer ends up being different. Solve the equation cosine of x equals 1/12. This trig function is already isolated, so I don't need to worry about that. So the first thing that I'm going to do is I'm going to find one solution to this equation using arccos. And I'm going to use arccosine to tell me one angle at which cosine outputs this given value of 1/12. The first thing that I'm going to do is I'm going to check the mode. So currently it's reverted to degrees mode, so I'm going to pop that back into radians, and I'm going to plug in 1/12. Then I'm going to evaluate arccosine at that value. So trig second cosine, and it says that the result is the angle 1.487 in radians. So this is one angle at which cosine outputs the desired value. So let's use the unit circle to find all the others. In this case, our desire is to make the x-coordinate equal to 1/12. So to make a mental note of that, I'm going to draw a vertical line in this picture labeled with x equals 1/12. But what the calculator just told me was that if I plug in the angle 1.487 radians, that's one way to reach this location in quadrant number 1 where the cosine outputs 1/12. So 1.487, or any coterminal angle, these are half the solutions to the given equation. But they're not all the solutions, because there's another location on the unit circle where the x-coordinates are also equal to 1/12, and that's this location down here in quadrant number 4. So based on what I've found so far, what angle do you think would get me down here in quadrant number 4 to this secondary location? Now turning counterclockwise through an angle of 1.487 radians is how I reach this location at the top. Due to the symmetry of this picture, if I want to get to the bottom, all I have to do is turn clockwise by the same amount. So that can be achieved with an angle of negative 1.487 radians. And with this, I get a description of all the other solutions. If I wanted to express this in shorthand, I could say 1.487 plus 2 pi k, or negative 1.487 plus 2 pi k, where k is in the integers. This would be shorthand for what's written in English above. These are the values of x that would make the given equation a true statement. Now to complete the set, let's solve the exact same equation, but this time with tangent instead of either sine or cosine. I'm going to start the problem in exactly the same way that I did before. I'm going to start it by finding one solution using, in this case, arctan. So putting myself back into radians mode, I'm going to enter the value of 1 divided by 12. I'm going to hit trigonometry second and select the inverse tangent function, and I get a value that's pretty similar to what I got from sine, which is 0.083 rounded to 3 decimal places. Now here's what makes tangent so special and different from either sine or cosine. To find the other solutions to this equation, what we're going to use is the fact that tangent repeats its behavior not every 2 pi units, but every pi units. Whereas the period of the sine and cosine functions was equal to 2 pi, the period of the tangent function was equal only to pi. So I'm going to take this singular angle, 0.083, but another can be found pi units away. Another can be found 2 steps of pi units away. Another can be found 3 steps of pi units away, and so on and so forth. So to sum up, my final answer to this question, in shorthand, would be 0.083 plus some integer multiplied by pi. Pi, or 2 times pi, or 3 times pi, etc. These are all the values of x at which tangent outputs 1 over 12. Tangent being very unique because it completely repeats every half of a rotation instead of every full rotation. Now for our final example, I want to show you a situation where when you get the equation, the trig function is not yet completely isolated. For example, in this exercise, the trig function sine of x exists on the left-hand side of the equation with an added 3 and a plus 2. So before I get started on any inverse signs or unit circle or anything like that, the very first thing that I'm going to do is I'm going to isolate sine of x. So to that end, the first thing that I'm going to do is I'm going to get rid of that added 3, and that leaves me with 2 sine x equals positive 1, and then to eliminate the 2, I will divide it out, and this leaves me with sine of x is equal to 1/2. Now, sine of x equals 1/2 is a little bit special, and is different from sine of x equals 1/12. And that's because 1/2 is actually a y-coordinate on our unit circle reference image. So that means that we can find the angles at which sine outputs 1/2 without necessarily needing to use a calculator and the inverse sine function. So looking back at this circle, at what angles does sine output a value of positive 1/2? The first such location is over here at this pi over 6 radians in quadrant 1. Over here to the left side of the unit circle, which is located at an angle of 5 pi over 6. So the solutions to this equation would be that the input of sine, x in this case, could be equal to pi over 6 or any full rotation from that angle, or the input x could be equal to 5 pi over 6, or any full rotation from that angle, where we emphasize that it has to be a full rotation. We cannot go half of a rotation or a quarter of a rotation and get the same output from sine. These are the inputs, these are the x's, these are the angles that would make the given equation true. That concludes today's material. Today we practiced using the unit circle in combination with the inverse trig functions to find all the solutions to an equation which contained a sine, a cosine, or a tangent. Generally speaking, the method was, first, isolate your trig function if it's not isolated already. Then, if necessary, use a calculator and the inverse sine, inverse cosine, or inverse tangent button to help you to find one solution to your given equation. In the case of sine and cosine, you now have been given one location on the unit circle with the specified either x-coordinate or y-coordinate. So then find the other location on the unit circle with the same x-coordinate in the case of cosine, or with the same y-coordinate in the case of sine. Then make sure that you are also accounting for any coterminal angles, which for sine and cosine will be 2 pi units away from the angles that you found on the unit circle. Tangent is a little bit special. For tangent, once you have found a single angle which outputs the desired value, then all you have to do is account for all the other angles which are pi units apart from the angle that you found using arctangent. That angle plus pi times k, where k is an integer.